Okay, good afternoon. Let's start perfectly on time. So last week we saw all these negative results, in particular errors in possibility and a couple of variants of errors in possibility. And then we were asking ourselves, so what can we do to get around these negative results? And I laid out a couple of different escape routes from errors in possibility and these related theorems that we are going to follow in the next couple of lectures. And what we are going to do today is to look at an implicit assumption of errors in possibility theorem. So if you think about implicit assumptions, what I mean here is that we are not weakening any of the axioms that have been stated explicitly in the theorem, like, I don't know, non-dictatorship or Pareto optimality. But we are taking one of these implicit assumptions, which is just part of the theorem, but it's not stated as an axiom. So one of these implicit assumptions could be that the number of alternatives is at least 3, for instance. So that's not an axiom, but we do know if there are only 2 alternatives, then Arrow's theorem does not hold, and we can, for instance, take majority rule and have a nice positive result. And the implicit assumption that we're dealing with today is considering the domain of preferences, because for errors in possibility, we did need that all possible configurations of preferences are possible. So all preference profiles are possible. And therefore, in today's lecture, we are going to look whether there are interesting subdomains of preference profiles for which the impossibility doesn't hold and for which we can get positive results. So I hope this is working. It sounds a bit different today, but I hope it works fine. So the escape route that we are looking at will give us a very strong positive results, which is great. But the assumptions under which we are going to get these results are rather restricting. Okay, so let's look at what we are having here. So as I said, so the implicit assumption that we have in errors in possibility is that D of U, which is the domain of preference profiles, is just the combination of every possible preference relation for each voter. So all preference profiles are possible. And by restricting the domain of preferences, of course, it may be possible to get more positive results rather than an impossibility. Just to give you an example of a restricted domain of preferences, so a very natural domain of preferences, which I'm sure I have mentioned a couple of times already, is the domain of strict or linear preferences, which we are going to denote by D-lin. Okay, so this is the notation for the domain of strict preferences. And what we are having here is that we have this set of preference relations. So previously that was R of U, which is just the set of all complete and transitive preference relations. Here L of U is the set of all complete, transitive, and anti-symmetric preference relations. So just strict preferences. So there are no ties anymore. And this is, of course, quite useful. And for instance, we already talked about the fact whether errors in possibility also holds if all voters have strict preferences. And the answer was yes, but it doesn't follow immediately from the theorem. So you have to look at the proof itself. Maybe just the formal definition of this here to make sure that you see what this is. So it's the subset of preference relations. So these are already complete and transitive with the extra condition of antisymmetry. That means if we have 2 different alternatives, and this person is indifferent between these 2 alternatives, they have to be the same alternatives. Okay, so we only have ties between an alternative X and itself. Okay, so the relation is still reflexive, but we cannot be indifferent between 2 different alternatives. Okay, so in general, so we will look at different domains of preference profiles throughout the next weeks. An important property of some of these restricted domains is whether they are Cartesian or not. Cartesian means that the preference profile, the set of preference profiles is built using the Cartesian product of the same set of preference relations for each of the agents. So formally, this means that the domain is defined using some subset of preference relations, R prime. Okay, R prime could be, for instance, L, which is the set of strict preference relations. And then the domain is just defined by mapping each of the voters. So this is the set of functions from the set of voters to the set of preference relations. In other words, so for all of the voters, we have some set of preference relations, and it's the same set of possible preference relations for each of the voters, and any combination of these builds an admissible preference profile. Okay, because what we want to have in the end is a domain of preference profiles. And the Cartesian domains are defined by just having one set of preference relations, which is the same for all of the voters, and then the set of preference profiles is just built using a Cartesian product, just like here. So it's the same set of admissible preference relations for each of the voters. So here, this also means that, so it's not only Cartesian, but strictly speaking, it's also symmetric, because we're taking the same set of preference relations for each of the voters. More generally, one could also define Cartesian domains by having different sets R prime for each of the voters. But here, for simplicity, let's just stick to this symmetric definition of Cartesian domains. So how about this domain of strict preferences that we just defined? So the domain of strict preference profiles that we defined, would that be a Cartesian domain or not? Yes? Yes, right? So it's guess it's pretty obvious from the definition now. So R prime then, of course, would be just L of U. Okay, but I think right on the next slide, we will already see a domain which is not Cartesian. Okay, and one thing that I already mentioned is that the proof of Arrow's theorem also works when the domain of preferences is the domain of strict preferences. And this is something we have also discussed, or I explained in the forum. So the statement itself, the statement that we proved for weak preferences doesn't imply the same statement for strict preferences, but if you look at the proof closely, you will easily see that all the arguments that we had in the proof of Arrow's impossibility theorem work exactly as they did before, also for strict individual preferences. So if you think about these, also in the exercises and tutorials, you have seen these, so we had these two different parts of the proof, so this field expansion lemma and the group contraction lemma, as they are sometimes called. And for these, we had certain preference profiles that we were arguing for, and all of these just had strict preferences. So if we have strict individual preferences, unfortunately, the same proof goes through. So this is not a successful example of this escape route, because if you have strict preferences, we still get this negative result, unfortunately. But I think it's a very nice and simple example of a restricted domain of preferences. Okay. Now, in order to get some more positive results, what we are going to do is we recall what the essence of Arrow's impossibility was, and that was that the majority relation can be cyclic. Before we had Arrow's impossibility, we looked at this Condorcet-May paradox, and we had this simple preference profile in which the majority relation was cyclic. And therefore, one can define a domain in which just cycles in the majority relation are ruled out in order to get more positive results. In particular, once we make the assumption that the majority relation is acyclic for all preference profiles, okay, so we just look at preference profiles which do not yield cycles in the majority relation. So this is a well-defined set of preference profiles. So it's maybe not as easy to write it down like the one where we just had strict preference relations for each of the voters, but it's a well-defined set of preference profiles. And if you only look at these profiles for which the majority relation is acyclic, well, then this max function, which takes the maximal elements of the majority relation from any feasible set, is a well-defined social choice function. What do I mean by well-defined? So by well-defined, I mean that it always returns at least one alternative, because that's what social choice functions and also choice functions need to do. And if there are no cycles, that we have seen in the first lecture, so this is really just lemma 1 from the, not the first lecture, the second lecture, which was the choice theory lecture. So there we proved that acyclicity is necessary and sufficient for always having a non-empty set of maximal elements. Okay, so that means if we just look at these subsets of preference profiles, then we already have a function that always returns a non-empty set of elements. And if furthermore, this majority relation is even assumed to be transitive, okay, there should not only be no cycles, but the majority relation should even be transitive, well, then this max function satisfies all conditions of Arrow's theorem, right? So if you think about the conditions, so we just take the maximal elements of the majority relation. So if we don't have majority ties, that would be exactly the Condorcet winner. So if there's a Condorcet winner, then we would return this alternative. Since we can also have majority ties at this point, there's something that is in the literature usually called a weak Condorcet winner, which is just an alternative such that there is no other alternative that dominates it using a strict majority of the voters. So the maximal elements of the majority relation are just, in the literature, also sometimes called weak Condorcet winners. And the function that returns those alternatives satisfies all of Arrow's conditions because clearly it's non-dictatorial, this function. It satisfies Pareto optimality. What else did we have? IIA, right? So it satisfies IIA because what alternative is being picked or which alternatives are being picked only depends on the preferences of the voters within the feasible set. We are just taking the maximal elements of the majority relation, and for the majority relation we only need to look at the pairwise comparisons within the feasible set. And also it is rationalizable. So this is usually something that was difficult to satisfy, but here it's straightforward just by the definition, right? So rationalizability means we pick the maximal elements of some underlying preference relation, and here it's explicitly given. It's just the majority relation. We just pick the maximal elements of the majority relation, and therefore it is rationalizable. Even more, this function does not only satisfy the axioms from Arrow's impossibility, it is also the only function to do so. And this is also straightforward, so this doesn't require a proof or anything, because, well, it is the only function that is rationalized by the majority relation, right? The maximum function is always a unique function. So we take the maximal elements of some complete relation, which in this case is the majority relation, and there's only one such function which satisfies this property. In other words, what this means is, so this is a very simple result, which, as I said, doesn't really require a long proof or anything, but we can just, for the sake of the example, we can take Arrow's impossibility, then restrict the domain of preference profiles to preference profiles for which the majority relation is transitive. Okay, as I said, it's a well-defined set of preference profiles. And then rather than having an impossibility result, we can even get a complete characterization of this max function, which only picks the maximal elements of the majority relation, if we slightly change the axioms to make sure that pairwise choices are made according to majority rule. Okay, so this trick we have used several times in the past, also last week and in the exercises. So if we take these axioms that we had for a Maze theorem, anonymity, neutrality, and positive responsiveness too, we know that pairwise choices have to be made according to majority rule. Okay, and if we impose these axioms on the social choice function, then we have fixed pairwise choices. The majority relation doesn't contain any cycles, so it is a well-defined rationalizing relation, and therefore we have a social choice function which satisfies all of Arrow's conditions, and it's even the only one. So we can take this negative impossibility theorem and convert it into a complete characterization of one single function, namely the function that always returns the alternatives which are maximal according to the majority relation. And by assumption, for all preference profiles that we look at, there are always maximal elements for the majority relation. Okay, to make this a bit more precise, let's define a domain which we call D-trans, which is the domain of all preference profiles. Okay, so this is again the set of complete and transitive preference relations with this extra condition that the majority relation should be transitive. Okay, so this is this well-defined domain that I mentioned earlier. This is a domain which is not Cartesian, right? So if you think about it, so Cartesian means that we have the same preference relations available to each of the voters, and any combination of these will form a preference profile which is in the domain. But that's clearly not the case here, right? So for instance, if you think about the Condorcet paradox, where we have these three preference relations, ABC, ABC, BCA, and CAB. So those three types. So of course, out of each of these three, you can build valid preference profiles for which the majority relation is transitive. For instance, if you have three voters who have preference relation ABC, so then the majority relation is transitive, right? So the majority relation is the same as the Pareto relation in this example. You can also have all three voters having the same preference relation, CAB, for instance, then the same would be the case. But if you take a combination of each of these, which would be allowed if this domain would be Cartesian, then also the Condorcet paradox profile has to be in this domain, which it is not. Okay, so this domain is clearly not Cartesian because it really, so which preference relation is allowed for which voter clearly depends on which preference relations the other voters have. Okay, so by the combination of all of these preference relations, make sure whether the majority relation is transitive or not. And then we have this theorem, which doesn't require a proof because it follows straightforwardly from the statements that we already have. If we restrict the domain to D trans, okay, so rather than having this domain, so previously this was our domain of preference profiles. So we make this smaller by only allowing preference profiles for which the for which the majority relation is transitive, then the function that returns the maximal elements according to the majority relation not only satisfies all these conditions here, but it is the only social choice function that satisfies these conditions, because those three axioms here, by May's theorem, make sure that pairwise choices are made according to majority rule. Okay, so the base relation of this function, because it has to be rationalizable, is majority rule. And well, this base relation rationalizes this function because it is transitive. Okay. So I think I do have a figure here where I explain how or visualize how this works. So here are the different conditions that we had for errors impossibility, non-dictatorship, IRA, Pareto optimality, and then here for errors it was transitive, rationalizability, or equivalently, this is what is meant by consistency, alpha and beta plus. So those four were inconsistent with each other, and then there's this implicit assumption that all preference profiles are possible. Okay, and then the idea is to make this assumption weaker. Okay, so we only allow less preference profiles. So we only study preference aggregation with a restricted set of preference profiles. And at the same time, we make these other conditions stronger. Okay, so as we did when we moved from Condorcet-May to errors impossibility. So rather than having non-dictatorship, we have anonymity. Here we have neutrality. And we only need these three conditions here to make sure that pairwise choices are made according to majority rule. And then if we have so these like 5 axioms give us an impossibility, and these 5 axioms here give us a complete characterization of this max function, which returns the maximal elements of the majority relation. Okay. So on the upcoming exercise sheet, we have like a statement which is almost a strengthening of what I showed you here. And because on this exercise sheet, we have a very nice new exercise where we have this condition and those here. So here we are not making these stronger and still get a complete characterization of majority rule. The only extra assumption that we need for the exercise is that the number of voters is odd. Okay, but this is a T exercise. So if in case you think this all sounds quite difficult, so you don't need to worry that much. It's a tutorial exercise. All right. So what we have seen now that, okay, in principle, maybe that's also not a big surprise, and I used lots of formalism to precisely show you what we are doing here, is that if we just rule out cycles in the majority relation, or if we even assume that it has to be transitive, then all these impossibilities don't hold. Okay, and for the rest of today's lecture, we will look at specific examples of domains of preferences for which the majority relation is not cyclic, or for which it is transitive even. So that means we are looking at subdomains of this domain here. Okay, and some of them are quite natural. Okay, so but before we get to look at these specific domains, some words about strategy proofness, because the nice thing about the functions that we are talking about today is not only do they get around errors impossibility, but they also are strategy proof. So strategy proofness we have discussed at the beginning of this course, and we will get back to strategy proofness every now and then. And I already hinted in the first lecture, I think that there's a very strong impossibility theorem using strategy proofness. So basically every reasonable social choice function can be manipulated. But if we restrict the domain of preferences, this is no longer the case. And it's just similar like the escape route that we are now taking from errors. We can get much more positive results if we restrict the domain of preferences. In particular, the functions that we are going to talk about today are strategy-proof functions, which means they cannot be manipulated strategically. And this all follows from one and only one statement for the functions that we are considering, because I said the domains that we are looking at will be subdomains of this domain here. So it suffices to take the maximal elements of the domain in which, well, this is well defined because we have a transitive majority relation, that this function here is strategy proof. It cannot be manipulated. That we are going to show. And then this means that the same statement will also be true for all subdomains of this that we are talking about. So this will be a universal statement that just requires like, I don't know, 3 or 4 lines as a proof. And then we will know that all the functions that we are going to talk about today are actually strategy proof. One thing to make sure when we are talking about strategy proofness is something that I discussed before already. So in general, so this can be several alternatives, right? So it's possible that a social choice function yields maybe 2, 3 alternatives at the same time, and then when we are manipulating or when one voter changes her preferences, we get a different choice set, and then it's not clear how to compare those. And that's why I think last time or the week before, I'm not sure, we defined strategy proofness for now by just saying that singleton sets can be compared and everything else cannot be compared. So something only counts as a manipulation if we get from one alternative A to another alternative B, and we like B strictly better than A. Okay, so if we go from one alternative A to a set ABC, it doesn't count as a manipulation at this point. So later on in this course, we will define variants of strategy proofness for set-valued functions. Okay, so now regarding this proof here, so we want to show that this max function is strategy proof whenever the majority relation is transitive. Okay, so that's our first statement for today. So strategy proofness. And it's actually quite straightforward. So I think most part of the proof is taken up by writing down the definition. So for strategy proofness, what do we need here? So we have two different preference profiles, which are the same, except that one voter changes his or her preferences. Okay, so we have two profiles, R and R prime. Okay, now we are specifically talking about the max function, which takes the max or returns the maximal elements of the majority relation. And since we can only compare singleton sets, we are assuming that in the original preference profile, there is a unique maximal element according to the majority relation. Okay, so as I said before, so there in terms of the true preferences, there's a unique winner, and then there's one voter which can change her preferences, and then she gets something which she strictly prefers to that. Okay, and then of course we have that these two preference profiles have to be exactly the same, except that voter I is allowed to change her preferences. And well, what is the goal of her changing the preferences? She changes her preferences and then she gets something that she strictly prefers. Okay, so we assume, it's basically contradiction proof. So we assume for contradiction that this function can be manipulated. So there's some other alternative that she prefers to A. Okay. So the original outcome is A, then she changes her preferences, and then the new outcome would be alternative B, which is better for her. And now, as I said, so the argument is relatively straightforward because the only thing basically that we need is that if the original outcome was just a singleton, and which is the main assumption that we are making here, the majority relation is transitive. Okay, what do we know then? Okay, so now let's think about the majority relation. So the single alternative which is not majority dominated is A. So everything else is dominated by some majority. Okay, and we know that this majority relation also is transitive. So any other alternative, C, D, E, has to be majority dominated by something. Okay, and then this other alternative also has to be dominated by something because only A is returned. So that means that if there's only a single maximal element and this relation is transitive, then alternative A has to strictly majority dominate all the other alternatives. Okay, so it has to be a Condorcet winner. So A strictly majority dominates all the other alternatives because we have to have a reason why each of these other alternatives is not returned. And this is where we are exploiting that only A is being returned. So all of the other alternatives are majority dominated by something. The relation is transitive, so eventually A has to majority dominate everything, all the other alternatives. In particular, and that's the only thing we need at this point, it has to majority dominate B. Okay? Not so everything else, including B, of course. And now the rest is really extremely simple because we have that in the original preference profile, a majority prefers A to B. And in the original preference profile, this voter I preferred B to A. Okay? And then this voter I can change her preferences in any way she likes. In particular, she can change her preferences between A and B. But if she changes her preferences between A and B, she can only make A stronger against B, right? Because in the original preference relation, she preferred B to A. So the only thing that she can do is make A stronger than B. And that means that this majority only becomes larger. And if she doesn't change her preferences between A and B, well, we still have this majority in favor of A versus B. Okay, so no matter what this voter I does in this new preference profile, we still have that A, so here it's the prime, so because it's the new majority relation of this other preference profile, the insincere preference profile where voter I is lying about her preferences, and here still a majority has to favor A versus B. Okay, and if that is the case, well, if B is strictly majority preferred, then B, of course, cannot be a maximal element according to the majority relation, because we have something else, namely A, which is strictly better. So we don't know what the choice set is of this max function, but definitely B is not going to be in there. Okay, but returning singleton B would be the only possibility such that this would be a successful manipulation, because this voter prefers A originally. She changes her preferences in some way, then the only thing that she actually prefers to singleton A would be singleton B, but that's ruled out. Okay, and therefore this function has to be strategy proof. Okay, so we would have a manipulation if you go from singleton A to singleton B, but here this is ruled out, and the simple reason for that is just we know from transitivity of the majority relation and the fact that A is a unique winner that a majority prefers A to B. Well, voter I originally prefers B to A, so the only thing she can change in the pairwise relationship between B and A is making A stronger versus B than it was before. Then there would still be a majority, okay? And therefore B cannot be selected, and that completes the proof. Yes? Oh, yes. Okay, thanks. Oh, and also I used this old notation here, right? And it should be equal, you're right. Okay, so the preferences of the voters are exactly the same, except that voter I's preferences are changing. Yes? Here? Okay, so here, so to be precise, quasi-transitivity would be sufficient. But so we are using it because we know that only A is, so if we only argue about the original preference profile here, okay, A is the unique winner. So that means all the other alternatives need to be strictly majority dominated by something. So let's say, so for instance, B needs to be strictly majority dominated by some other alternative. Otherwise, B would be returned. B would be a maximal element, right? So the set of maximal elements is just everything that is not strictly dominated. So it could be that B is strictly majority dominated by some C, okay, but then C again would also be strictly dominated by something because it's also not returned there. And if we have a path like this, then we know in the end that A needs to strictly majority dominate everything, not only B, but all the alternatives there. So, and that's where we need transitivity. Okay. And actually the fact that, so as maybe let's use this here. So this is an important assumption, otherwise the theorem wouldn't hold. And as I said, quasi-transitivity suffices. And interestingly, acyclicity does not suffice for the statement, because acyclicity would still be enough to make sure that max is a well-defined social choice function, right? So this is what we had in this choice theory lecture. So if the majority relation is acyclic, then we can always pick maximal elements. But if we only have acyclicity here, it turns out that there are functions, or that the max function can be strategically manipulated. So you can go from singleton A to singleton B. And this is actually an upcoming homework exercise to show this. But we are already telling you which preference profile to look at, so which makes this a bit easier. But the homework exercise essentially is to show that, that this cannot be replaced with acyclicity. Okay. Other questions? Yes? No, I don't. I didn't have any assumption. So because we're now talking about a specific function, we are talking about the max. So this statement, so the theorem that we are proving is that this max function satisfies strategy proofness, and the max function does satisfy IA. That's right. Okay, but it's a bit simpler than that because we are talking about one single function, right? So we, of course, so max does satisfy IIA, but we know exactly what max is doing. So here, for instance, and also here, we used exactly how max is defined. So not only do we know that it satisfies IIA, but we know exactly how it is defined. So it always just returns the maximal elements of the majority relation. But you are right about the fact that it does satisfy IIA. Yeah. Yes? Okay. Okay, so we made this assumption because the way we define strategy proofness for now is that it has to be a manipulation from a singleton to another singleton. Otherwise, it doesn't count as a manipulation. Okay, so because we had this problem that when defining strategy proofness, we don't know how to compare sets. That's why defined it in the most conservative way we could think of. If you manipulate from A to B and you like B better than A, that's a manipulation. If in the original, if here you had like ABC or something, then we don't know how to compare sets. That's why it's not a manipulation. That's why we could make this assumption here. Yes? Okay, yes. So for let me think about this. So for any number of alternatives, I'm not sure. So if we have only two alternatives, we had the statement that monotonicity is equivalent to strategy proofness. So by the way, the question was whether every social choice function that satisfies positive responsiveness is also strategy proof. So for two alternatives, positive responsiveness is stronger than monotonicity. Well, in any case, it's stronger than monotonicity. And we have shown that monotonicity and strategy proofness are equivalent for two alternative sets. In general, no, it's not the case. Okay, now I can think of an example. If you have more than two alternatives, then there are functions that are positively responsive, which are not strategy proof. And that function would be Border's rule. Okay, so Border's rule can give you a single winner, and it is positively responsive. So I think that was, I'm not sure whether we mentioned it at that point, but it's clearly positive responsive. So if there is some tie between several alternatives and we make one alternative stronger, then this alternative will be the unique winner afterwards. But Border's rule can be manipulated. But in general, so it's a good question because there are connections between monotonicity, positive responsiveness, and strategy proofness. Okay. Unless there are no more questions, let's get back to strategy proof social choice in general. So that means if we have this domain in which the majority relation is transitive, then picking the maximal elements of the majority relation gives us a strategy-proof social choice function, which is pretty nice. And we are going to apply this theorem to several domains that we are studying today. Now here comes a nice theorem which we are not proving. So we were thinking about using this as a T exercise, but the proof is a bit like too tedious. So let me just give you the statement here. So we can define a variant of D trans, which is just defined for strict preference relations. Okay, so D trans was just the set of preference profiles for which the majority relation is transitive. And here we take the intersection of D lin and D trans, and that just means we look at strict preference profiles for which the majority relation is transitive. Okay, and the idea here is just that if we look at strict preference profiles for which the majority relation is transitive, and we also assume that the number of voters is odd, so that means we have strict preferences, an odd number of voters, and that means for pairwise comparisons for two alternatives, there can be no ties. There can be no majority ties between two alternatives, because if everybody has a strict preference and there's an odd number of voters, well, of course, we have to have a majority going in one way or the other. There are no majority ties. Okay, and furthermore, it means if the majority relation is transitive, is that each preference profile will admit exactly one Condorcet winner, right? Because the majority relation is transitive. There are no majority ties, and that means for every preference profile there will be a unique Condorcet winner. So we know Condorcet winners are always unique when they exist, but in this domain there's always a Condorcet winner, and that means that this max function is even resolute. Okay, so resolute, just as a reminder of functions that always return a single alternative. So this domain is particularly nice because it always gives a single alternative, which also makes the statements about strategy proofness nicer, because we don't have to get around comparing sets or something, because if there's always a singleton winner, then we know exactly how to compare these singleton winners. And for this particular domain, we have a nice statement. Okay, so here, so these are some justifications for this statement here. So if we have an odd number of voters with strict preferences, then the majority relation is anti-symmetric. This is just what I said, so there can be no ties. It's still transitive, because we are talking about transitive majority relations, and therefore there's always a unique maximal element, and that is the Condorcet winner according to this preference profile. Okay, and then the statement by Campbell and Kelly for this domain here is that if the number of voters is odd and we are looking at this particular domain, then max is the only non-dictatorial Pareto-optimal strategy-proof and resolute social choice function. Okay, so here before we showed that max is strategy-proof in this domain here, but this here is a complete characterization, so it means there are no other functions which are strategy-proof. And these extra assumptions here are basically just there to make sure that we don't have majority ties. So if we rule out majority ties, then there's this nice theorem which says just always returning the Condorcet winner, which is guaranteed to exist by the domain assumption, is the only strategy-proof function which also satisfies these really minor conditions here, like non-dictatorship, Pareto optimality. So these are basically Arrovian conditions here, right? So that's why this statement is quite nice. Okay. So much on strategy proofness. Now, as I said, so we are going to talk about concrete domains of preference profiles, which allow for positive results. And the first one is an extremely simple domain. It's the domain of dichotomous preferences. And as the figure here is supposed to illustrate, dichotomous preferences just means that you have only two indifference classes for your alternatives. So either you like something or you don't like it. Okay, it's just thumbs up or thumbs down. So it's not that you only have a unique choice which you like. You can like everything in the feasible set, but it's in particular impossible that you have a strict ranking of three alternatives, like A, then B, then C. So that's not allowed. Dichotomous means you have only two indifference classes of alternatives. So formally, so again, formal definitions always look more complicated than what they intuitively mean. But of course, they are important to make sure that we are talking about exactly the same thing here. So we take a preference relation from the set of all complete and transitive preference relations. And then we say that for every triple of alternatives x, y, and z, if x is preferred to z, so if x is strictly preferred to z, if x is strictly preferred to y, then this third alternative z has to be indifferent to x or indifferent to y. Okay, so this condition makes exactly sure that we only have two indifference classes. So if we have three different alternatives and we like x better than y, then this third alternative has to be on the same level as x or on the same level as y. And if this holds for every triple, well, then the preference relation has to be dichotomous. Okay, and here again is the informal definition of this domain of preference profiles. Okay, so I guess you can, so in many settings, I think you can imagine that people might have preferences like these. It is a somewhat simplifying assumption, but also there are some like applications where people only have the ability to express their preferences in that way. So you cannot submit a complete ranking of alternatives, but you can only say that you do like some alternatives and you don't like all the other ones. And the nice thing about this domain is that the majority relation is transitive for every preference profile in this domain. Okay, so this would be an example, our first example of a domain for which we have like concrete positive results. So if we have dichotomous preferences, the majority relation is transitive, and that means returning the maximal elements of the majority relation gives us a function that satisfies all of Arrow's conditions and even much stronger ones. It's a strategy-proof function, as we have shown previously, right? Because that's just what we showed before. And all we need to do in order to get these results is to show that the majority relation is transitive. So basically what we are doing here, I don't know if I cannot really draw these calligraphic symbols very well. So we are showing that this domain is a subdomain of, okay, this is an H, of the trans domain, okay? So where we have transitive majority relations. So this here is equivalent to that. Okay, we only need to show that the majority relation is transitive. Okay, and the proof for this is also not too difficult, but it gives some nice intuition how we can prove transitivity of the majority relation. Okay, so we have now this assumption of dichotomous preferences. And we want to show that the majority relation is transitive. Okay, and this becomes a little bit easier if we introduce some extra notation. So for any alternative x in the universe, we define, so maybe let me first just write down the formal definition and then you tell me what this is. So we define n of x, which is a number. Okay, so it's a natural number and it's defined like this. So it's here we take the intersection for all y's in U. And here we have nxy. Okay, so nxy is a notation that we introduced earlier, which is also on your cheat sheet. It's the set of voters who prefer x to y weakly. Okay, so this is what nxy is. Okay, and now we take, for every alternative y, we take the intersection of all of these sets of voters who prefer x to y, and then we count how many elements this set has. Okay, it's a set of voters, so we count voters which have a certain property. So what would that be? So what is, intuitively, what is n of x? Exactly. So it's the number of voters who have x on the first place, or top ranked. Right, so it doesn't mean that's uniquely top ranked. So there could be other alternatives on top as well, because nxy is just the number of the set of voters who prefer x to y weakly. But this is just one way of formally writing down the number of voters who have x on top. Top rank x. Okay, and now that we have this notation here, we can think about the majority relation. So because eventually what we want to show is that the majority relation is transitive. So that means if there's a majority who prefers x to y, and there's another majority who prefers y to z, then there's also a majority who prefers x to z. Okay, so let's first look at what this here means. Okay, so x is weakly preferred to y according to some majority of voters, just by definition. So I'm just filling in the definition here. Just means that the number of voters who prefer x to y is at least as large as the number of voters who prefer y to x. Okay, so that's very straightforward. And And this holds not only for dichotomous preferences, but for preferences in general. But now we have the special case of dichotomous preferences. Okay, so if we have dichotomous preferences and we are interested in the pairwise comparison between x and y, there are basically 4 different possibilities. So there are voters who, like, let's call it approve already. So we can call alternatives that are being top-ranked approved ones and ones that are not top-ranked disapproved ones. So there are voters who approve x and y. There are voters who prefer y to x. There are voters who disapprove x and y, so who don't like any of these alternatives. And there are voters who prefer y to x. Okay. Now, here, this is the number of voters who weakly prefer x to y, and this is the number of voters who weakly prefer y to x. So that means all these here, all the voters that have these preferences, we are counting on both sides here. Okay, so we can just subtract them and ignore them here. Then these 2 types are voters who weakly prefer x to y. Oops. Let's make it a bit nicer. Who weakly prefer x to y. And well, the ones here in the last column, so these are definitely ones who do not weakly prefer x to y, because they strictly prefer y to x. And therefore, for dichotomous preferences, we have that this is the case if and only if the number of voters who top rank x, so these are those 2 different types of voters, have to be at least as large as the number of voters who top rank y. Right? Okay, because we have looked at these 4 different types of voters. So these are the ones who top ranked x. And in order to check whether there's a majority in favor of x versus y, we only need to check whether there are more voters who top ranked x than voters who top rank y. Okay, so this only works for dichotomous preferences, of course. So here, this only works for dichotomous preferences. Okay, and once we have this, so this is really like, yeah, I guess one could make this proof a bit shorter, but so once we have this here, it's pretty straightforward, because we want to show transitivity of the majority relation. And now we have a direct relationship between the majority relation between x and y and the number of voters who top rank x and who top rank y. Okay, and that means that for transitivity, as the precondition, we have x is preferred to y by majority, and y is preferred to z by some majority. Now, if we just fill in what we have just stated here, well, we have that nx has to be at least as large as ny. Okay, so this is really very detailed, but let's just do it completely. And ny is at least as large as nz. And of course, so since all of these are just natural numbers, we have that nx is at least as large as nz. Okay, just by transitivity of this greater or equal relation here for natural numbers. Okay, and then okay, so there's not enough space here. Or there's space. And this, by this equivalence here, is exactly the same as saying that x is majority preferred to z. Okay, and this is what needed to be shown. So we knew that we had these 2 relationships between two pairs of alternatives, and then as a consequence, we show that a majority prefers x to z, which completes the proof for transitivity. Okay, I hope that this is quite straightforward. And that means that the majority relation, in the case of dichotomous preferences, is transitive. So we can always pick the maximal elements of the majority relation. Any ideas of, if we have dichotomous preferences, what would be the alternatives which are maximal according to the majority relation? Because we now know that one alternative majority dominates another one if nx is at least as large as ny. Okay, so we do know that there are always maximal elements according to the majority relation, but we don't want to draw the majority relation for the dichotomous preference profiles. Right? It's much simpler to identify the winners, the maximal elements, because we know this here. So this is the same as x being majority preferred to y. Okay, so which would be the maximal elements according to the majority relation if we have dichotomous preferences? So it seems like you only need to look at how many times an alternative is top ranked, yes? Okay, but so depending on this number, and then we take the alternative which is top ranked most frequently, right? So for which is top ranked most often, and that would be like a maximal element according to the majority relation. So that follows directly from this here. So that means rather than really drawing a majority graph or something, we only need to check how many times an alternative is approved by each of the voters, and we just return those alternatives, it could be more than one, which are approved most often. Okay, so and that I think if you think about dichotomous preferences is also the natural thing that you would do, right? So if you assume that everybody has only approved and disapproved alternatives, it seems like a very natural idea to pick those alternatives which are approved most often. And these are exactly the maximal elements according to the majority relation. That is just what we have shown here. And that means, okay, so here I need to go forward a bit. This is what we have just shown. And that means that we have, for the simple domain of preferences, of dichotomous preferences, we have a very like natural and simple social choice function that satisfies all the nice conditions. So this function formally returns the maximal elements of the majority relation, but it's much easier to just see, we just count how many times each alternative has been approved by the voters, and we return those alternatives that are approved most often. And this social choice function is called approval voting. It's a very practical and simple and nice method. So many rules that we are going to study in this course will be much more complicated than this one here. And I think this is like one which can be really proposed for practical use immediately. And it's definitely much better than plurality. So in the beginning of the lecture, we had all these problems with plurality, where you can only basically just approve a single alternative. But here you can just approve any number of alternatives and just pick those alternatives that are approved most often. So it's almost as simple as plurality, but it gives much better results. And it was, so you may wonder why something like this even has a name, because it's like in many polls, for instance, you have multiple choices that you can make, and then the answer that has been clicked on most often will be the answer that is being returned. But there's actually several books that study approval voting in detail. So here we made this simplified assumption that preferences are actually dichotomous, but you can also use approval voting in settings where preferences are not dichotomous, but voters just have to submit these dichotomous ballots. Okay, so the votes that you have to do is just that you approve something and disapprove something, or the other alternatives. But in reality, for instance, you could have like strict preference relations. So this introduces strategic effects, because then it's not clear which alternatives you would approve and which ones you don't. Therefore, here we studied only under the simplified assumption that preferences are actually dichotomous. And if you really only have dichotomous preferences, then this function satisfies all the nice properties you could think of. So these two persons here on the slides are Stephen Brahms and Peter Fishburne. So Stephen Brahms is a political scientist, and Peter Fishburne was a mathematician, so he passed away last year, unfortunately. And they both were big fans of approval voting, so they wrote a book about it, and they really suggested it to many organizations and wanted it to be used in real life. So there's even a list of organizations that are using approval voting. But it turned out that even for a simple rule like this, some people have reservations because, like, changing, in particular when it comes to voting, changing anything away from the status quo is difficult, because the persons who got elected using the old method don't want to change that, because they think they're going to get re-elected by the old method again. And then also there are sometimes like misconceptions. For instance, sometimes an argument that is often repeated for not using approval voting is that it goes against this simple rule of one man, one vote, or the more modern version would be one person, one vote. And because sometimes people claim, so the more alternatives you approve, the more voting power you have. So if you only approve one alternative, you have less power than somebody who approves 3 or 4 alternatives. But of course, that doesn't really make sense, because if you approve all the alternatives, you're completely irrelevant. You don't change anything. But sometimes this is being used against approval voting. Okay, yeah, so as I said, so this is a very nice and simple method, but of course the underlying assumption that preferences are dichotomous, and that is the assumption that we were making here, is quite restrictive. Okay, so it's completely ruled out that there's a person who strictly prefers X to Y to Z, for instance. So that's just not a possibility. Okay, somewhat recently, so like 4 years ago, a city in the US, Fargo, became the first city to adopt approval voting for all local elections. So there are some little success stories, but given that I think this book on approval voting is several decades old, yeah, sometimes people would wish that these progresses would work a bit faster than they do. And the formal statement here again is just because we previously proved that whenever the majority relation is transitive, so in any domain in which it is transitive, then returning the maximal elements is a strategy-proof function, and this is just a special case of that. So the domain of dichotomous preferences is a subset of the domain of preference profiles for which the majority relation is transitive, and therefore this function is also strategy-proof. So you cannot manipulate in approval voting, again, under the assumption that your preferences are really dichotomous. Okay, so if they're not really dichotomous, and if you actually have a ranking of the alternatives, then of course you can strategize on which alternatives you approve and which ones you don't, and there are many studies about this. Also, maybe to underline the practicality of this thing, so in particular when it comes to manipulation, I mentioned some time ago that, for instance, in these US presidential elections, there are frequently these third candidates, apart from the main nominees by the Republican and the Democratic Party. So for instance, in 2016, 6 years ago, there was, apart from Clinton and Trump, there was also this third party candidate, Johnson. And that I gave you as an example where clearly that voting strategically is a reasonable thing to do, because otherwise your vote is just wasted. If you had approval voting here, and for instance, you do like, in this example, Johnson better than Clinton and that better than Trump, so which is like a preference relation, presumably of many voters, then you can just approve both Johnson and Clinton, and you still can express your preferences and try to get a better outcome in the end. Okay, so guess that's all I'm going to say about approval voting, unless there are questions. So it's really just, I think, a very simple domain, simple results, and a very simple rule, which works well under quite restrictive assumptions. Okay, so then let's move on to single peak preferences, which is another example of a domain for which we will get nice and positive results. So I think dichotomous preferences and single peak preferences are the prime examples of preference restrictions which allow us to get away from errors in possibility. And the idea for single peak preferences is as follows. So assume that the different alternatives in a social choice setting are maximum income tax rates for some fictitious country. Okay, so the voters get to elect what should be the maximal income tax rate in a given country. So just to make things simple, there could be 5 alternatives. It could be 20%, 30, 40, 50, and 60. So it's just very crude, but it's just like a toy example. And if you had a set of alternatives like this, then there are certain preference relations that may seem a bit weird. Right? So you would probably find it really strange if somebody says my most preferred alternative is 20%, and then it's 60, and then it's 30, and then it's 50, and my least is 40. Right? So that seems a bit strange, and because intuitively what you would expect is that each of the voters has like a top choice which they think would be the ideal tax rate, and then if you move away from this top choice, your preference is decreasing. Okay, and hence the term single peaked. So the special thing about this set of alternatives is that there's a natural underlying linear ordering of the alternatives. So here they are just numbers, natural numbers, 20, 30, 40, and so on. And then you would expect, so of course it's a restrictive assumption, but you can make the assumption that if preferences can be ordered like this, that you have some top choice among this axis. And then if you move away from the axis, then your preference only decreases. And this is exactly what single peak preferences are about. So you want to rule out things like what I said in the beginning, that you like 20 the best, and then 60, and then 30, and then 50, and then 40. So that would not be a single peak preference profile, because you would have two different peaks if you draw this. And here I give you an example which hopefully illustrates this a bit better. So if we have these 5 different alternatives and, for instance, 3 different voters, then you could, for instance, have a voter like Alice who thinks 40 is the best tax rate, and then 30, and then 50, and then 20, and then 60. Okay, so in the example here, come on. Alice is depicted by this blue line here. So this is a way of depicting preferences. One thing that you have to make sure is that, so on the y-axis we have the order of preference, but no intensity, right? So it's still just ordinal preferences. So whatever we have on top here is the most preferred alternative. So 40 is the most preferred alternative of Alice, and then it's 30, then it's 50. So each of these lines gives the different ranks that the voters can give to the different alternatives. And if you just draw a line through these different alternatives according to this axis here, well, here you can see that this preference, this depiction of the preference relation is single peak, because there's a peak here, and then the preference is decreasing if you move away from the peak. Okay, to give another example, for instance, here there's Bob here, who thinks 50 is the best tax rate, and then 60, then 40, then 30, then 20. Okay, again, if you look at this, this would be a single peak preference relation. Or there can be Charlie, who doesn't like taxes at all, thinks 20 would be the best maximum income tax rate, and then the higher the tax rate gets, the least he prefers it. That would also be a single peaked preference relation. Okay, so I haven't given you a formal definition yet, but intuitively I hope it's clear what is meant here, right? Note also that your preferences do not only depend on the peak, right? So for instance, it could be that here Alice prefers 40 the most, and then we could exchange 30 and 50 here in a preference relation. So move this down and this one up, and it would still be single peaked. Okay, so that would also be a single peak preference relation. So the preferences do not only depend on the peaks, but we have this extra assumption that if you move away from the peaks, then the preference can only decrease. So if you move away here, so alternatives can only get worse. And the same if you go to the other side here. Yes? Okay, that's a good question. So there are definitions of single peakness for indifferences, but so there will be several parts in this course where we make the simplifying assumption that preferences are strict, and this will be one of them. So we are going to define single peak preferences, just in the example, only for strict preferences to keep things simple. But there are other models where preferences can also be weak. So that's one of the reasons why I introduced this D-lin in the beginning, so the domain of linear or strict preferences, because many results get much nicer and easier to understand if you restrict attention to strict preferences. Okay, yes? Okay, so you mean if alternatives cannot be compared to each other? Okay, so you mean, okay, so if you think about like US presidential elections and these 3 candidates, I haven't said that everything works in the single peak model, but you might ask the question whether preferences in US presidential elections are single peaks. And one example that is used in political science sometimes is that you can arrange candidates on the left-right spectrum. Of course, it's a much simplified assumption. But there are these classical left-right spectra where you go from liberal to conservative. More sophisticated models, which I will also discuss later after the break, I guess, have more than just one dimension. But one motivation for looking at single peak preferences is that this ordering here, so here it's extremely natural, the ordering that you get in terms of the tax rates. If you have 5 parties in Germany, for instance, you could have a much simplified ranking or ordering of the different parties, where you have the most left party with Die Linke, for instance, here, and then you have Die Grünen here, and then SPD and CDU and AfD, for instance, on the right-hand side. So that would be a spectrum that probably many people would agree with, but of course it's a very crude simplification, so there are sometimes more aspects that get into account here. But it's a domain restriction. So for some examples, I think it's pretty straightforward, like here. For other ones, like political parties, it's usually not as easy as that. Of course, yeah. That's why it's a restricted domain. So if there is some linear ordering of the alternatives according to which the preference profile is single peaked, then we are fine. But in many applications, we will not find such a linear ordering of the alternatives. But for some, so I will give other examples later. So for instance, it could also be if it's budgets that should be spent on something. So how much money should be spent for a library, for instance, at the university. Okay, so then the different alternatives would be different amounts of money. And there you would expect that most people have single peak preferences, that they don't have something like, so either we should spend everything or nothing. That seems a bit strange there. So, but maybe before the break, let me just quickly show you the formal definition so that you have some time to think about this. So the formal definition, again, as mentioned earlier, formal definitions are just take some time to being parsed and understood. The formal definition of the domain of single peak preferences first depends on the linear ordering. Okay, so we first have this linear ordering, which would here, for instance, be the natural ordering of these tax rates. Okay, so 60 is greater or equal than 50 and greater than 40 and so on. So this is a linear ordering on the alternatives. It's not a preference relation, so it's just the ordering defined on the alternatives. It could also be the political left-right spectrum, for instance. And then according to this ordering, we have the domain of single peak preferences, which is the domain of preference relations, of strict preference relations. So here L, so this is why here, where it is visible that we are restricting attention to strict preferences, such that the following holds for all triple of alternatives. For any triple of alternatives x, y, z, if the linear ordering, okay, so this is the ordering of the alternatives, is x, y, z, or z, y, x. So the condition is symmetric. So if we exchange left and right, so it shouldn't matter. So if we exchange the highest and the lowest tax rates, single peakness should still be satisfied. So if the ordering of the alternatives is x, y, z, or the other way around, whenever somebody prefers x to y, she should also prefer y to z. Okay? And this is just because if we are moving away from the peak, so if x is preferred to y and the ordering is like this, we know that z is even further away from x, and therefore the preference has to decrease. And the same goes in the other direction. If x is preferred to y, then y has to be preferred to z because we can only go further down. Okay, so this is just the formalism that defines preferences exactly like they are depicted here. So there are, of course, examples of preference profiles which are not single-peaked. For instance, the Condorcet paradox profile is perhaps a simple one where you can easily check that this preference profile is not single-peaked according to any linear ordering of the alternatives. But in many examples, you can have these single-peak preferences, and there you will get positive results. So what we are going to show after the break is that within each of these domains, so this is actually a class of domains, for any linear ordering, we have such a domain. The majority relation will be transitive. So again, it will be similar to what we did previously. Actually, more precisely, we are going to show that it's quasi-transitive. But that means that we will always have maximal elements. We can take the maximal elements, and then we will have lots of good results. So if preferences are single-peaked, this is another example of a domain where we can circumvent errors in possibility. All right, so let's have a break now and start again at, I don't know, 5:40. Okay. And then study single peak preferences in more detail. And now, come on. We discussed a little bit possible applications. So as I mentioned before the break, so in some applications it probably doesn't really make much sense. So it really depends on whether there's a natural ordering of the alternatives given by the application. So I did mention already the left-right political spectrum that is being sometimes used in order to argue for single peak preferences. You can also think of examples where you want to locate some facility on a one-dimensional axis, like a road, for instance. So there's a road, and then you want to place something that people like a shopping center. Not sure whether everybody likes shopping centers, but if you want to live close to a shopping center, then your preferences would probably be single-peaked because you yourself have a location on this road, and you prefer a shopping center to be as close as possible to your own place. Or it could also be, I don't know, a police station, for instance. If it's a rough neighborhood, you want the police to be as close to your own place as possible. Another example that I like quite a bit is like having a temperature for a joint thermostat. So if you're working in a joint office, like maybe 5 people are working there, then you can have an ideal temperature that you would like for the thermostat, but you can only set one temperature for everybody. That's why you have to aggregate your preferences in order to make a collective decision. And that would also seem, maybe it's a good example for today, because as I said, it's really cold in here now. Probably most of us would agree that it could be a bit warmer, but the ideal spot for the temperature is probably different between us. And there you would assume that preferences are single peaked. So there, again, there would not be this extreme example where somebody says it should either be 10 degrees or 30. These are my favorite choices. And then you can think of many other examples where you have some kind of linear ordering of the alternatives. So it really depends on whether you have structure on the set of alternatives. So it could be this tax rate that we discussed earlier, the size of a public park, for instance, which you would also expect preferences to be single peaked. So like a city decides on how large a park should be in the city center. Budget of a library I already mentioned, and school grades I think is another good example. So if you want to aggregate grades, and once we talk about strategy proofness later, this will also be an interesting point. So if you have like a group of examiners, professors who are like grading a student, then they can have different grades for the student, and here or ideal grades that the student should get in the end. And if they need to aggregate their preferences, you would also assume that these preferences are single peaked, so that you think that this is really like should be a 2.3 or something, and then your preference for other grades decreases if you move away there. So I guess you can also think of many other examples. The important fact is just whether you have this natural ordering of the alternatives. And then, of course, well, we wouldn't do this if there wouldn't be a nice theorem to prove. And the theorem here is that the majority relation, if preferences are single peaked according to a given linear order, is quasi-transitive. Okay, so it's slightly different than before, where we had transitivity. Here we only have quasi-transitivity, but as you know, quasi-transitivity is still enough to have maximal elements. So that means we have a nice function for which we can just take the maximal elements of the majority relation. And this function also satisfies all kinds of other nice properties. And this is what we are proving. Let's make some space here. So this is like the main proof of today's lecture, I would say. Single peaked prefs. Okay, what needs to be shown is the following. The majority relation is quasi-transitive. That means if a majority strictly prefers x to y. Okay, and there's also a strict majority in favor of y against z, then it is also the case that some majority prefers x to z. Okay, so this is what needs to be shown. In particular, so this statement, like all these transitivity statements, is the statement about triples. So for every triple, so I didn't write down the quantifiers here to save time and space. So for every x, y, and z, the following should be the case. And now how do these x, y's, and z's differ now that we know that preferences are single peaked? So they differ in how they are ordered according to the linear ordering that is given for the single peak preference domain that we are studying. Okay, so and that's why we are looking at different cases. So for instance, it could be that on this one-dimensional axis we have x, y, and then z, or we could have y and then x and then z. So there's the total number of orderings of 3 alternatives is what? Just to keep you awake. So we have 3 alternatives. How many ordering of 3 alternatives are there? Strict orderings? Yes, there are 6. And for single peakness, because it's symmetric, as I mentioned earlier in the definition, we can just summarize. So that would be 6 different cases then. So it could be x, y, z, or z, y, x, for instance. But it doesn't matter whether it's x, y, z, or z, y, x. So we can always summarize 2 of these cases in one case. So we are going to study 3 cases here. And for each of these cases, we are going to show that the majority relation is transitive. More precisely, for 2 of the cases, we are showing that it's transitive. For the 3rd case, we are showing that the case is impossible, so that we cannot have something like this. Okay, so let's start with case 1. Okay, so here the ordering, now this is a bit tricky because now I have to make sure that this is like really a straight symbol. So this is the greater symbol, which is used to denote this linear ordering here. So we have x, y, z. So it's not a curly symbol, not a preference relation. Or it's the other way around, z, y, x. So those two cases are completely, can be handled in the very same way. That's why we are summarizing those. And how do we start here? So the first two cases are quite similar to each other. So we again use this notation here, nxy. Okay, so nxy is the set of voters who prefer x to y. So it's who weakly prefer x to y, but now for single peak preferences, we are only considering strict preferences. So we had L of u, so that means preferences are always strict. So we know that the voters who weakly prefer x, or who strictly prefer x to y, and for which the alternatives are ordered like this, what do we know about these voters, about their preferences over y and z? Right? If you now recall the definition, or maybe let me switch back here. So this is the definition of single peakness. So we have, if the ordering is x, y, z, and there's a voter who prefers x to y, then this voter also has to prefer y to z, right? So that's exactly the definition of single peakness. That means, so here we have an entire set of voters, all the voters who prefer x to y, and they do have single peak preferences, and the linear ordering is like this. So all of these voters have to be voters who also prefer y to z. Okay? And we can write this down by just having this subset relation. Okay? So all the voters who prefer x to y are also voters who prefer y to z. And this is precisely where we used single peakness. So that's why I switched back to the definition, because we used that the ordering is just like this, or like this. Then it would go in the other direction. Okay, so now we know that the voters in this set prefer x to y, and they also prefer y to z. What do we know about their preferences about x and z? Okay, so let's assume you are a voter who prefers x to y, then you also have to prefer y to z. How about x and z? Yes? You also have to prefer x to z, but the reason is just that your individual preferences are transitive, right? So if you prefer x to y and you prefer y to z, then you also prefer x to z. Right? Your individual preferences are transitive. I'm not talking about the majority relation at this point, because that's what we want to show, that the majority relation is transitive. That we don't know yet, but we know that each voter's preferences are transitive, because we always assume that voters' preferences are transitive. So anybody who prefers x to y and prefers y to z, well, also has to prefer x to z. Okay? It's just transitivity, and I'm emphasizing that it's transitivity of the individual preference relation, because, well, I will just write down trans here, but really make sure you remember that this is transitivity of the individual preference relations, not of the majority relation. And that means that all the voters who prefer x to y are also voters who prefer x to z. Okay, now we are already done with the first case. Okay, so why is that true? So we want to show that, so we do know a majority prefers x to y and a majority prefers y to z, and we want to show that a majority prefers x to z. So this is what we want to show. This is the consequence we want to show, okay, for transitivity. And now we know that all the voters who prefer x to y also prefer x to z. Okay, so how many voters prefer x to y? Well, we don't know how many, but we know that it's a majority. Okay, and all of these also prefer x to z, so the majority can only become larger. Okay, so that means strictly more than n over 2 of the voters have to prefer x to z, and that's why we have a majority here. Okay? So let's just write what I just said. So now we take the cardinality of these sets, so the number of voters who prefer x to z is at least as large as the number of voters who prefer x to y. Okay, so this really straightforwardly follows from the statement before here. If everybody who prefers x to y also prefers x to z, then this number here, so the cardinality of this set can only be at least as large as the one of this set here. But we do know that the number of voters who prefer x to y is a majority. Okay, and therefore this cardinality also has to be a majority, and we are done. Okay, so we have shown that this is the case, and this proves that here. Okay, is that clear? So that is case one. So we assumed this, and then we showed that this has to be the case. Under the assumption that the linear ordering of the three alternatives is one of these two here. And now for the next two cases, we have to look at the different orderings that are remaining. So as you said, there's a total of 6 orderings. That's why we are also looking at the other 4 now. I'll give you some time still, so because the next case will be similar, but so you better make sure that you have followed these kinds of arguments here. Okay, so here we used single peakness, transitivity of the voters' preferences, and the rest is really just counting. And we know that this is a majority. Okay, yeah. Yes. Okay. So this relation here. So this here, as I emphasized before, is not a preference relation. So it's this what I call the linear ordering of the alternatives. So the tax rates, for instance, that could be, and that's why we have to look at all 3 possible enumerations of these 3 alternatives. Okay. All right. So now let's look at the second case. Okay, so we can take them in any ordering, but here I'm doing it that it's z, x, y, or the other way around, which would be y, x, and then shouldn't be curly because it's really a greater sign, and z. Okay, so now for this other ordering of these 3 alternatives, we again have to show the same implication here. So we can make these 2 assumptions and have to show this consequence here. Okay, so we start with the voters who prefer z to x. Okay, so it's just like we did before. So here we looked at the voters who prefer x to y. And then by the definition of single peakness, we know that those also have to prefer y to z. And now the beginning is exactly the same. So we look at the voters who prefer z to x. Those also have to prefer x to y. And then by transitivity, z to y. Okay, so here again, we have single peakness. nxy. And then by transitivity, we have that nzx right, is a subset. Okay, so I have to do exactly what we did up here, only with different letters here, is a subset of nzy. Okay, so it's just transitivity. A voter who prefers z to x and x to y also prefers z to y. And that's why this is a subset of this here. And then the rest is only a bit more tedious now, because we want to have these orderings the other way around, because we want to show that there's a majority in favor of x versus z. So we want to show that this here is a minority. Okay, because we have strict preferences. So if this here is less than n over 2 voters, then nxz would be strictly more than n over 2 voters. So in order to make this more precise, we start with n over 2. We know that the cardinality of nzy is less than that. So why do we know this? So now we use this here. A majority prefers y to z. So a minority prefers z to y. Okay, so this number has to be strictly less than n over 2. Okay, and then now we have, okay, now we can use exactly this inclusion here. And we have then nzx. Okay, and that means that the number of voters who prefer z to x is less strictly less than n over 2. Okay, and that means because we only have strict preferences that the number of voters who prefer x to z has to be strictly larger than n over 2. And this is precisely, this is precisely what we want to show. We want to show that the majority prefers x to z. And this is exactly what is written down here, because preferences are now assumed to be strict. Therefore, we have nxz is strictly larger than n over 2. Okay, and that completes the second case. So it's almost completely analogous to the first case here. Okay, now there are two cases, or like two orderings remaining, which we can deal with in one single case. The first one is the linear ordering yzx. So this one is missing. And the opposite ordering, x, z, y. Okay, and again, the beginning is exactly like we did before. So we know the ordering goes y, z, x. So then we look at the voters who prefer y to z. And we know that all those voters, because of single peakness, also have to prefer z to x. And then transitivity again gives us that all those voters have to prefer y to z. Okay, so the beginning is exactly the same, but here now we will get a contradiction in the end, so which shows that this case cannot occur. Okay, by single peakness, we have here that this is a subset of nzx. Okay, and then transitivity. So the nice thing about this proof is it's a bit repetitive. So if you had trouble understanding like the first case, I'm repeating it 2 times, which hopefully makes things clearer, because it's the same arguments here. So we now have nyz is a subset of nyx, okay, y and x, so by transitivity. Okay, and now we use what we already know about the majorities between these 3 alternatives here and write a chain of inequalities like we did in the previous case, for instance. So here we start with n over 2, and we know that the number of voters who prefer y to z is a majority. So this is precisely this assumption here. We know that this is a majority. But now by this inclusion here, this implies that the number of voters who prefer y to x has to be at least as large. Right? Okay, so the number of voters who prefer y to x because of this inclusion has to be also a strict majority. Okay, but if there's a majority in favor of y versus x, then there has to be a minority who prefers x to y, because we have strict preferences. Okay, but it's not possible that a minority prefers x to y, because here the assumption was that x is preferred to y by a majority of voters, not a minority. And therefore this case cannot happen. So this sometimes happens with case distinctions, that you look at several cases and then you prove that one of these cases can never occur. nxy is less than n over 2. Okay, and this is a contradiction to our original assumption. So what this last case means is that, so here we fixed the ordering of the 3 alternatives x, y, and z. So we wanted to, for any triple of alternatives x, y, z, we wanted to show transitivity by ordering them exactly like this. And then we permuted, or we looked at all possible linear orderings of the alternatives. And what we have just shown is that if this is the case here, then it's not possible that the linear ordering looks exactly like this. So this just cannot happen. So that only leaves the first 2 cases here. And for those 2, we have shown the consequence. And therefore, transitivity is satisfied. Okay, so this assumption here is incompatible with this assumption here. That leaves these 2 cases here. And in those 2 cases, we have exactly shown the consequence, which is this statement here. Yes? That's basically, let's go back to the definition here. If you look at the definition of, so the question was, again, let me repeat it, was why these pairs of cases are equivalent to each other. So if you look at the definition of single peakness, so the definition of single peakness is already symmetric. Here we say that if the ordering is x, y, z, or it is z, y, x, then this consequence has to hold. So if we invert the ordering of these three alternatives, the consequence is exactly the same. So, and this corresponds to going either to the left or to the right in this diagram. And the definition of single peakness doesn't make a difference whether we go to the left or to the right. We're only saying that if we go to one end of the spectrum, then the preference has to decrease. Okay, or maybe if you maybe want it a bit more formally, so here we have if it's x, y, z or z, y, x, then this is the consequence. Okay, so now try to recall this term in parentheses here. And this is exactly what we used here. So here the ordering was x, y, z or z, y, x. And then for both of these linear orderings, the consequence was that everybody who prefers x to y also prefers y to z. And that's why this inclusion here holds for both of these cases, just by the definition of single peakness. Okay? And here we are doing exactly the same, only that alternatives have different names. Other questions? Okay, so it's like talking about this proof. So I think there's one of these cases. So it's that's actually quite nice how this works out. And then sometimes these proofs for showing transitivity of the majority relation can be a bit tedious because you have to look at many different cases here. There was one tutorial exercise that we skipped this year, which had even more case distinctions, and that was just tedious. But once you have understood one of these steps, you basically have understood what's going on in the other two as well. Okay, and notice also that we were really using only quasi-transitivity here. Okay, so the transitivity of the strict part of the majority relation. That's actually something that might be like a nice exercise. I don't think we have it on the exercise sheet, but we are showing that the majority relation is quasi-transitive if preferences are single-peaked. So you might wonder what happens. So can't we also show that the majority relation is transitive? And this is not the case. So you can come up with a simple example. It only requires 2 voters. So that might be an additional exercise in case you're interested in that. You can find a simple 2-voter example where preferences are single-peaked, but the majority relation is not transitive. It's only quasi-transitive. Okay, so we had these distinctions in the beginning of the course where we have had simple examples where relation is only quasi-transitive but not transitive. Okay. In case you're interested about this 2-voter example, you can also ask in the forum and then we can discuss it there. Okay, now what we have shown is that the majority relation is quasi-transitive. And come on. And there's also another class of domain of restricted domains for which almost exactly the same proof goes through as well. And that's the domain of single caved preferences, which are sometimes also called single troughed and single dipped preferences. Here the idea is exactly the other way around. So you have one sweet spot, which is the alternative that you like the least. And then if you move away from that sweet spot, your preference only increases. So single peaked looks something like this. So there's some unique peak, and then your preference is decreasing. A single caved, it's exactly the other way around. So for instance, you could think of the one-dimensional road example there, where you want to place a facility on a one-dimensional road, and it's something that everybody hates, like a garbage dump or something. Or maybe a police station, if it's a neighborhood of criminals, for instance, they don't want to live next to a police station, then your preferences could be single caved. Okay, and maybe it's not completely surprising that basically all the results that we have for single peak preferences also work for single caved preferences because it's like a natural dual case. So if you're interested, you can look at the proof again and then realize that also for single caved preferences, the majority relation is quasi-transitive. Okay, what we are now seeing is something very nice, and that is that's similar to what we had with dichotomous preferences in approval voting. So we proved for approval voting that the majority relation is transitive. And then I said we don't really need to draw the majority relation in order to find the maximal elements. There's a very simple way of finding a maximal element according to the majority relation for dichotomous preferences, which is just to count the number of approvals. And there's something similar, easy, for single peak preferences. So if we know that a preference profile is single peaked, we could, for instance, just draw the majority relation and then identify the undominated alternatives as the ones that need to be chosen. But there's a much easier way of identifying the maximal elements, and this is called median voting. And under the domain, or under any domain of single peak preferences, the social choice function that returns the maximal elements of the majority relation is known under the name median voting. And in order to make things even simpler here, we are, on this slide at least, we are making the additional assumption that the number of voters is odd. Okay, so we have seen another example before the break where we made this assumption. We will make this assumption more and more frequently throughout this course because it simplifies matters quite a bit. So maybe some of you, I'm not sure, have taken this course before. So in previous years, in this lecture, we had something that we called the declaration of oddity, where we made the assumption that the number of voters is odd throughout the rest of the course. So I've changed this a bit this year because some statements actually require an even number of voters. So here we make it more precise when we make this assumption. But the main reason for having an odd number of voters, in particular if we have strict preferences, is that we cannot have majority ties. Okay, and this we have already seen previously simplifies matters by quite a bit. So whenever I talked about taking the maximal elements of the majority relation, if there are majority ties, there can be several of these. Right? So we could have 10 alternatives, majority ties between all these alternatives. So that means there would be majority indifference between all the alternatives. So max would return all 10 alternatives. If we have an odd number of voters with strict preferences and the majority relation is transitive, then there can be exactly one maximal element. Right? Because there can be no ties between the alternatives. It's a transitive relation, which means it's a strict ranking of the alternatives in terms of the majority relation. And that is also quite nice in the context of single peak preferences. If we assume that the number of voters is odd, then this max function only returns a single alternative. And that is the Condorcet winner, of course. Just like before, where we had this D-trans domain, where the majority relation is transitive. And we also made this assumption that there's an odd number of voters with strict preferences. So that was D-trans plus. Then there's exactly one and only one alternative that is the maximal element according to the majority relation. And so if we make this assumption that n is odd, then there's a Condorcet winner in every preference profile. So that means not only does this function satisfy nice properties, as we have discussed earlier, but it's even a unique winner. So there are no ties anymore. Okay, and then the question is just, so how can we find this Condorcet winner? Because I said earlier already, we don't need to draw the majority relation and see which alternative only has outgoing edges. So there's a much more convenient way of identifying the Condorcet winner. And this has to do with the linear ordering of the alternatives. Because if we have this natural underlying ordering, then the Condorcet winner has certain properties which makes it much easier to identify this alternative. And in order to understand how we can identify the Condorcet winner, we define this extra notation here, which is Ti. So this is for voter I. It's the top choice of voter I from feasible set A. So the feasible set is fixed for now. You can just assume that A is fixed. And then Ti is the top choice of voter I. And since we have single peak preferences, it means it's the peak of voter I. Okay, so for every voter, we look at the peak. And now I'm claiming the following. So if we have two different alternatives, x and y, such that y is greater than x according to this linear ordering, and there's no z that is in between. Okay, so there's no z such that this holds, just means that they are adjacent to each other. So we have two alternatives that on this one-dimensional spectrum are right next to each other. So, so we have x and y, and then we could have other alternatives here. But on this one-dimensional spectrum, they are just next to each other. Then I'm now claiming that x is majority preferred to y if the number of voters whose peak is weakly to the left of x is strictly larger than the number of voters whose peak is weakly to the right of y. Okay, so this is the linear ordering of the alternatives. And now the blue dots are the peaks of the voters. Okay, so these are the most preferred alternatives. Now, if we know that some voter, let's just draw some circles here. So for instance, this would be a voter whose top choice is this alternative here. What do we know about this voter's preferences between X and Y, if preferences are single peaked, according to this linear ordering here? Yes? Exactly, X is preferred to Y. So every voter who's weakly to the left of X prefers X to Y. So there could also be a voter who's such that this voter's top choice is X. Then this voter would also strictly prefer X to Y, right? Because this is the peak of the voter, and then we are just moving away from the peak. Okay, so all the persons whose top choice is weakly to the left of X prefer X to Y, and all those voters, maybe let's use a different color here, whose top choice, there could also be several voters who have the same top choice. All voters whose top choice is weakly to the right of Y prefer Y to X. So that means in order to identify whether a majority prefers X to Y, we only need to count how many voters' top choices are weakly to the left of X and weakly to the right of Y. Okay? Okay, so this allows us to compare alternatives that are adjacent to each other. Okay, so if, for instance, here we only need to count the top choices, and then we could also do this here. And we do know there's a Condorcet winner, right? So we do know if there's an odd number of voters, there's exactly one Condorcet winner. So that means there has to be some alternative which has like majority edges going in both directions. And we do know that the majority relation is transitive. So that means if you compare these adjacent alternatives, then we also have majority preferences like this, right? So if this is alternative X here, and a majority prefers it to Y, and then we also have a majority who prefers Y to Z, then by transitivity of the majority relation, there's also a majority who prefers X to Z. And we do know that such a Condorcet winner always has to exist, and that means that if we want to check whether some alternative is a Condorcet winner, we only need to count how many voters are weakly to the left of X and how many are weakly to the right of X. All right? And somebody is a Condorcet winner if the number of voters that is weakly to the left of X is strictly larger than n over 2, because then this alternative is majority preferred to everything on the other side. And it also has to go in the other direction. So the number of voters whose top choice is weakly to, I don't know which one would be left or right here, depending on how you interpret this. But if we only need to look at the top choices on the other side of this alternative X here, and this also has to be strictly larger than n over 2. And this is what I meant, that there's a very easy way of identifying a Condorcet winner. We only need to look at the top choices of the voter, and there need to be as many peaks to the left of this alternative than to the right. And here you can see why this is called median voting, because we are just identifying the median of the peaks. Right? So for each of the voters, we are looking at the different peaks, and we need to find a peak such that there are as many peaks on the left-hand side as there are on the right-hand side. And then this alternative is precisely the Condorcet winner, which is guaranteed to exist. Okay, so this here directly follows from this observation here and transitivity of the majority relation. Okay. Yeah, maybe let's do an example here. I think to make this absolutely clear. So for instance, if we have 5 alternatives and the ranking of the alternatives is like this, so this is the linear ordering, and there's one, so each of the voters has a different peak. Okay, so there's one who likes A the best, and one who likes B the best, and then one for C, D, and E. Then the Condorcet winner obviously would be alternative C here, right? Because the peaks that are weakly to the left of C are 3, which is like more than n over 2. It's more than 2.5, so it's a strict majority. And the number of peaks that are weakly to the right of C would also be 3, which is a strict majority. Okay, so then this would be the unique Condorcet winner. So let's maybe do another example, more interesting one, where, for instance, we have one voter who likes A the best. Then there are two voters who like B the best. Then for C and D, nobody has these alternatives as their peak. And then there are two voters who like E the best. Okay, so which alternative would then be the Condorcet winner? So we only need to look at the peaks of the different voters' preferences. And now we need to identify an alternative such that the number of peaks on the left-hand side is exactly the same as on the right-hand side, weakly speaking. Okay, or in other words, the median of these 5 different samples. So which alternative is a Condorcet winner if we have 5 voters with preferences like these? So 1 likes A, 2 like B, and 2 like E. B, right? Exactly, because if we have B here, well, then there are 3 alternatives that are weakly to the left of B, and 3 alternatives that are weakly to the right of B, and that's both of them are a strict majority, and that's why it's the median. So a simpler way of just doing this is just drawing it like this, and then we just, so if we have 5 voters, we need to count the number of voters from left to right, and we stop at the 3rd voter, because that is exactly the middle. If we have an odd number of voters, and there you can also see why we need an odd number of voters, because then we have uniqueness of the Condorcet winner. So if we have 5 voters, we count 1, 2, 3, and 1, 2, 3. It could also be the other way around. It doesn't matter how we order these 2 here. These voters are different, but the top choices are not. So the top choice of the median voter is the Condorcet winner. And there are several nice things about this. So the first one is that it suffices to know the top choices in order to identify the Condorcet winner. Right? So because I emphasized before the break, I think, or maybe it was at the beginning, after the break, I emphasized that, no, it was before the break. I emphasized that the top choices, you can have the same top choices, but different preference relations. Right? So I had this example with Alice, Bob, Charlie. It could be that you have the same peak, but then your preferences between the other alternatives can differ. So there are different single peak preference relations according to the same order with the same peak. But in order to identify the Condorcet winner, they're irrelevant, which makes this much easier, because if you have single peak preferences, there are different possible preference relations for the same peak, but all you need to state is just the peak. So it's almost like plurality. Right? So it seems like it's really simple, because you only need to have unique top choices, or you only need to look at the top choices and then can identify the winner. But what is quite striking, I think, is that if you change this example that I drew here a bit, so let's add 2 more voters, so that we now have 7 voters. One of them likes A and the other one likes E. What would be the median then? Okay, so now we have 7 voters. What would be the Condorcet winner if preferences are single peaked, like in the example on the left-hand side here? Okay, I think for some it seems like it's too easy, but okay, so it's still B, right? So the median is still B. Also, intuitively, if we go from the first profile to the second, if we add 2 voters at the extremes, then the median doesn't change, right? So we have one who prefers something to the left and one who prefers something to the right. Then the median would still be B. So alternative B is the Condorcet winner. But what is striking about this example, that if we would have used plurality, which only counts the number of times each alternative is top ranked, then plurality would return alternative E. So that means even in the special case where preferences are single peaked, which guarantees us transitive majority relation, so we have a strategy-proof social choice function and all nice properties, even then plurality fails because it picks an alternative that is different from the Condorcet winner. And that is perhaps a bit surprising, that plurality in essence is so bad that even for this very restricted domain of single peak preferences, it does something strange. So I think I've already talked about some of the bullets that are here. Okay, so like the simplest way of identifying the Condorcet winner is just drawing the top choices like this and then just counting from left to right and then count until the n plus 1 over 2 voter. Okay, so if the number of voters, if n is odd, then of course this is like an integer number, And this is then the top choice of the median voter, which is the Condorcet winner. The top choice is sufficient to compute the Condorcet winner. It's an important lesson. So we don't need to know all the preferences. The top choices suffice. And the plurality winner may be different from the Condorcet winner, even if preferences are single-peaked. And this is, for instance, what is shown in this example here. Okay, so this is the Condorcet winner. And I don't know, let's take this one here. This would be the plurality winner. Okay. And similar to what we had in the case of dichotomous preferences and approval voting, in the single peak domain, max is known as median voting. So as approval voting was known in the dichotomous domain. And one final thing, median voting satisfies strategy proofness, because as we have shown in the beginning of this course, so whenever the majority relation is transitive, and here we have strict preferences and it's transitive, then this median voting function is strategy proof. And it always returns a singleton, so it's pretty cool, right? So it always returns a single winner, it's strategy proof, so you cannot manipulate, and it satisfies all of the conditions in the impossibility theorem. So I think, for instance, one example where you see that how nice this is and that it should be used more often. Median voting is, for instance, when you think about aggregating grades. So I had this example where there were examiners who had different grades in mind for a student. So what is being done in practice in many times is just take the average, right? So there are 3 professors who are grading a student, and then you take the average in the end. But this is not strategy proof, as you can imagine, right? So it's if you can just exaggerate your grade in order to get something which is closer to your peak, right? So you have this ideal grade, so you think that this student should get it too. And then if you know that the others have very bad grades for the student, you can just claim to have a 1 for the student, and then this student will get a slightly better grade, so it will be closer to your peak. So you can manipulate the average. But the median you cannot manipulate. If you just take the median grade, then this directly follows from what we have proven there, but also intuitively it's clear. So you cannot misstate your preferences in order to get something that you like better. Okay, so that leaves basically one problem for the rest of today's lecture. Okay, so before we get there, there's this thing here. This is something what I already hinted at before. Yes? I'm not sure I got what you meant. So you're talking about the linear ordering of... Yes, so we have different lines for each voter, but but the linear ordering is the same for all voters. So the linear ordering of the alternatives, so like the political left-right spectrum, or this is the same for all voters. Yes, but there is no preference for this ordering. So you're taking offense with the fact that we're only taking into account the top choices, rather. Okay, yeah, it seems like this is so for identifying Condorcet winners, this is not necessary. Yeah. So if you only want to find an alternative that is majority preferred to everything else, it doesn't matter what your preferences about non-top choices are. Yeah, but it may seem a bit strange that this is not necessary, but that's just a matter of fact which follows from the analysis that I showed before. But I see your concern. Yeah, it seems a bit weird that we don't need. So because it means, so if Alice, like in the example that I showed you, if Alice switches, so she had this top choice, I think at 40% tax rate, and then I said if she switches her preference between 30 and 50, then there's different preference relations, but the Condorcet winner will be the same, according to what I just showed you, right? So you can change your preferences between non-top choices, but still the Condorcet winner will be exactly the same. Okay, so this figure here just meant to illustrate so that, of course, in real life, especially if you talk about political elections, it's not as easy as just having one left-right spectrum and you can place all the candidates on this axis. And therefore, this domain of single peak preferences doesn't solve all our problems because in many settings, we don't have this single axis. But for instance, for aggregating grades or tax rates or like monetary budgets, for instance, it seems quite reasonable. Right, and the last thing that I would like to do for today is an algorithmic problem because it's computational social choice after all, and we didn't have that many computational questions so far. And And a very interesting computational question is checking whether a preference profile is single-peaked. Right? So because we have now realized that if preferences are single-peaked, then things are nice. So we can try to study the algorithmic problem of, given a preference profile, is this preference profile single-peaked? So can we answer this question in polynomial time, for instance? So it really depends on how we ask this question, because so if this linear ordering is given, then the question is easy to answer, right? So if we know the ordering, we can basically we can draw the preferences as I did in this illustration there, and we can just check, does it look like it is single-peaked? So if the ordering is given, this is a simple problem. So algorithmically, this problem only becomes interesting if we don't know the linear ordering. So given some preference profile, does there exist a linear ordering of the alternatives such that the preference profile is single-peaked according to this linear ordering? Okay, so that is, I hope everybody agrees with, a well-defined computational problem. The input would be a preference profile, and then the output would be it's single-peaked or not. And ideally, if we have an algorithm, it would be nice if the algorithm also outputs the linear ordering according to which the preference profile is single-peaked. Okay, because that could be nice in some applications. For instance, if you have a preference profile and you don't really know the ordering according to this one-dimensional axis, but you can check whether the preference profiles are single-peaked according to one linear ordering of the alternatives. And the most naive way that you could try to solve this problem is try to enumerate all the different linear orderings. Yes? Yeah. L of U is the set of linear orderings, yes. So we had. Yes. Okay. Now that's a good point. So we always used only the strict part of this, and L of U is the set of strict relations of linear orderings. The only reason why this greater or equal sign is used here because of reflexivity. So x is greater or equal than x. Okay, so if you compare this to this relation here, then these two relations are exactly the same except for reflexivity. Okay, but if you miss the part that L of U is the set of strict preference relations, then you may think that this is actually a weak ordering of the alternatives that allows for ties, but that's not the case. Yeah, so it's just a strict ordering, and these two relations are exactly the same except for reflexivity. Okay. Okay, so we have to find a strict. So in this algorithmic problem, the question is just to find a strict ordering of the alternatives according to which a preference profile is single-peaked, or in the other case, output that this preference profile is not single-peaked for any ordering of the alternatives. And what I was just going to say before you ask this question was, well, just to have some algorithm, we can have an algorithm that just enumerates all these possible linear orderings, and then for each of these checks whether the preference profile is single-peaked, right? So what would be the biggest drawback of this algorithm? Pardon me? Yes, the complexity, right? Because the number of linear orderings is of course exponential in the number of alternatives, right? So we have m factorial strict rankings of the alternatives, and so for 4, that would be 24 different rankings, linear orderings of the alternatives. Maybe you could do it, but if we give you a homework exercise where you have to do it for 10 alternatives, it can be very time-consuming if you're using this naive method of just enumerating all the different possible linear orderings. So it would be nice if we can get some computational insight into this in order to ideally maybe even solve this problem efficiently. So this preference profile that I drew here as an example, I'm claiming is not single-peaked, and I can see that immediately. So it's obvious that this preference profile is not single-peaked. Does anybody have an idea why that could be the case? I mean, for any ordering of the alternatives A, B, C, D. Okay. Exactly. So you had the same idea? So okay. So it's if a preference profile is single-peaked, no matter what the ordering is, the least ranked alternatives by the voters have to be at the end of the spectrum, right? So no matter where your peak is, what you hate the most has to be the leftmost or the rightmost alternative. But here we have 3 different alternatives at the bottom, and therefore the preference profile cannot be single peaked. So, but what you said is right as well, but in general, so like a necessary condition for a preference profile to be single peaked, I think that we can agree on definitely, is that the number of bottom ranked alternatives has to be at most 2, because otherwise it cannot be single peaked. And that will be useful in general to checking single peakedness. Now let me see, in the interest of time. Okay, so let's summarize the first observation that we made. So the last ranked alternatives lie at the leftmost or rightmost position according to the linear ordering. So that's why we have this nice necessary condition of only having 2 different last ranked alternatives. Okay, so there's like another observation that we can make, which we can then develop or use and build an algorithm for checking whether a preference profile is single peaked. But in the interest of time, I think it would be not good to try to start with this algorithm now. But the thing that I'm already revealing now is that we will have an efficient algorithm. It's even a linear time algorithm that can check for a given preference profile whether it is single peaked or not. And if it is successful, it will not only say yes, but it will also output the ordering according to which the preference profile is single peaked. And maybe just as a hint, so you can already think about how you can develop such an algorithm. So this argument here basically shows is that these bottom ranked alternatives, they have to lie at the end of the spectrum. So a very nice idea is to just construct this one-dimensional ordering of the alternatives by taking the last ranked alternatives, then putting them on the ends of the spectrum, and then develop the spectrum from outside to the inside. Okay, because once we have removed these 2 alternatives, we take the next 2. If there's now 3 bottom ranked alternatives, we know that we're already stuck. So if there's only 2 at each step, we only need to make sure whether which put 1 to the left and 1 to the right. So there's another necessary condition which we have to check in order to see where we have to put these 2 alternatives. But the algorithm that we are developing will be one where we order the alternatives from the outside to the inside, and then in the end we can tell whether the preference profile is single peaked according to this. But the details of this algorithm are too much to do them in 5 minutes. That's why I will stop at this point, and we will start with this algorithm in the next lecture. And then in the next lecture we will continue to talk about restricted domains by giving a complete characterization of Cartesian domains for which the majority relation is transitive. This will be our final positive result for restricted domains, and then we move on to the next escape route from errors impossibility next week. Okay, thanks for your attention and see you next week.